Okay, so I want to go over the special senses. So the first sense that we're going to start off with is vision. So we have general senses, which are it's spread throughout the body. So, uh, what do you feel throughout your body, right? You feel pain, you feel temperature, you feel movement, you have chemical composition of body fluids. Special senses would be like hearing, smelling, because you only have one nose, right? While your whole body, you can feel pain in your leg and you can feel pain in your arm. And special senses require a specific stimulus, so things that you consciously perceive, and it triggers your automatic nervous system. So it's in the brain. So things like olfaction, tasting, vision, hearing, equilibrium, all things are included. So your eyes actually allow you to see electromagnetic spectrum. So you're only able to see the visual light. Other animals can see more, but with humans, you can't see as much. So this is the surface anatomy. So we have eyelids, right? So the eyelids protect your eyes from foreign debris and it helps you prevent light from stimulating your photoreceptors when you're sleeping. And you have pupillary fissures, which is the space between your eyelids. So it's where the eye pokes through. So it's a deep crevice. But a commissure is where the eyeballs meet. So your eyelids actually controlled by two facial muscles. The levator palpebrae superioris muscle, which lifts and levitates the eyelid, and the orbicularis oculi muscle, which is around the eyes and allows you to close your eyes. And you see this green plate? This is the tarsal plate. It's connective tissue within the eyelids, and they have tarsal glands embedded in them. And it secretes sweat in the eye and prevents sticking. So you have conjunctiva also, and yeah, and this one lines the eyeball eyelids. So people, you see a lot of people that have like a lot of blood vessels and their eyes are kind of like bloodshot. It's because they have a lot of conjunctiva that has dilated blood vessels. So you have pulmonary conjunctiva, which secretes mucus in the inner portion of the eye so it doesn't damage the eye. And you have the bulbar conjunctiva, which secretes directly on the surface of the eyeball. And eyelashes and eyebrows are kind of like used to prevent foreign stuff from going to eye. So we have lacrimal apparatus, which is lacrimation, which is the process of forming tears. So it sits in the lateral superior border of the orbit of both eyes. So it sits in the bony depression. And basically the steps is okay, I'm gonna draw it out for you guys. Let me get it. So first step, the lacrimal gland, let me draw it. So lacrimal gland, right, makes lacrimal fluid. Okay. And the fluid moves through the lacrimal ducts and spread across the surface of the eye, like that. And the tears then collect in the superior and inferior canaliculi. And it goes down to the nasolacrimal duct, which goes to the nasal cavity, which goes to the nasal concha. In the nasal cavity, the tears mix with the nasal mucus. And these tears, sometimes they evaporate and because like small, like you don't really see as much lacrimal fluid because they're like disappearing. And it also it kind of drains in your it kind of drain your lacrimal duct too. The ones that are left. But you don't really notice it. Okay, so we have the intrinsic eye muscle. So we have these allow you to kind of to move your eyeballs. So we have the superior rectus. So when one contracts, it pulls your eyes upward in the orbit. And then we have the inferior rectus. So when it pulls, it tilts your eyeballs down. And we have two oblique muscles that run diagonal, one on top and one on the bottom. And it kind of helps you twist and turn your eyes. So we actually have different parts. So we have the sclera, which is the outer layer. It's white and fibrous. It protects the eye and provides attachment points for all the intrinsic muscle. We have the cornea. Oh, and this was also made out of dense irregular tissue. We have the cornea, which is the clear window that allows light inside the eye, and it gets oxygen from air and absorbs. and all the nutrients are from the aqueous humor, which is constantly being replaced. We have the vascular tunic. It's the middle part of the eye. It's a lot of blood vessels. It has a choroid coat, which is the pigment layer on the back. And there's lots of melanocytes around here. They produce pigments and absorb excess light. And it prevents light from bouncing around the eye. So if you don't have melatonin, you kind of have blurry vision. So we have vascular tunic. The ciliary body is made up of ciliary muscles and tissues that secrete aqueous humor. And it holds the lens in place. The ciliary muscle focuses on the lens, and the lens is held by suspensory ligaments. So zongular fibers that go from the ciliary muscles attach to the lens and hold it to a suspend on the center. So if you use the sensory muscles, it can focus and move the lens so you can see things far. And the aqueous humor, it's like it brings the nutrients to the oxygen and it feeds the lens, cellular body, iris. And there's a lot of melanocytes in this area, which can reduce light reflection. And the sensory ligaments, they pull on lens, they flatten it out, and they focus on different areas. So the vascular tunic is a tin-colored muscular part of the eye anterior to the ciliary body. It's made of connective tissue and smooth muscle. So it's like there are colored ring of muscle, so it's kind of shaped like a donut. And we have the retina. These have photoreceptors that talk to a nervous system. It's connected to the optic nerve and it has the macula lateral, which is the yellow depression at the back of the retina. And we have the fovea centralis, which is the center of the macula lateral. It's a place where you have the highest density of photoreceptors. And the optic nerve kind of exits laterally. So optic disc is this area right here. So optic nerve goes first and then it's the optic disc. It's where the blind spot is, so there's no photoreceptors there. So if you try to focus light on that area, you can't see. So the interior of the eyeball. So we have the interior cavity, which has the posterior and anterior chamber filled with the aqueous humor, while the posterior cavity is filled with the vitreous humor that is and basically its function is it holds the eye in shape and it cannot be retina cannot be replaced. So, when you get older, like you kind of start to lose volume in that area. Okay, so image formation. So what essentially happens here is the light, right? Okay, let me draw it out. The light, right, goes first. It bounces, it bounces off the object and it goes to the cornea, which is the outside right here. And this is the first step. So it goes to the cornea and then it will go to the pupil, which is this area right here. And then it goes to the lens, which then goes to the retina. Okay, so let me read it out for you guys. So light goes through the cornea, it goes to the anterior chamber of the anterior cavity of the pupil. Then it goes to the posterior chamber, which hits the lens. Then it goes to the vitreous humor of the posterior cavity and hits the retina. And then the lens focuses the image by inverts the image as it goes through your lens. Your lens flip over the image and you see it upside down. So it also triggers nerve impulses that travel to a visual sensory area of the brain to interpret what you see. So the steps, light had to bounce off the tree, goes to the cornea, pupil, lens, retina, optic nerve, occipital lobe of the brain, and gets interpreted. Let me clear this. Let's move on. So nearsighted is myopia. The eyeball is longer than it should be. It isn't round. You can fix it by wearing like glasses or like concave lenses because it bends the light. So I can hit the retina at the right point. But if you're farsighted, your eye's too short. Where retina, you want to put a convex lens in front of your cornea. So it's too long, right? So the concave lens kind of helps focus the retina while it's too short. You want to add like extra like width so that it can be longer so that it can help you see better. Okay, let's look at the ear anatomy. So we have the tympanic membrane, which separates the external and the inner ear. And this is also known as an eardrum. It's very thin. It's fibrous connective tissue with collagen and elastic, so it's very stretchy, very resilient. The inner surface is made out of mucous membrane and is made up of simple cuboidal epithelial. And we have two layers of epithelium sandwiching a connective tissue in the middle. This is where it is. Okay, so also have, okay, so this is the tympanic membrane. Okay, these are cerebrum. They're kind of like modified sweat glands. They trap debris, and if you rupture it, it can easily rupture your tympanic membrane. So it is filled with air and three auditory ossicles. Okay, so they have one, the malleus, which is over here, two, the incus, and three, the stapes. So, and it also has a oval window, which is between the stapes and the inner ear, which is a thin membrane. And the round window is slightly smaller than the oval window and is covered by the secondary tympanic membrane, which relieves ear pressure. We have the so this is like what I was saying. This is the size of it. So stapes, incus, malleus. So um we're gonna get into the middle ear. Okay. So it allows the auditory tube is right here, right? It allows air from the tympanic cavity to outside by going through nose and mouth. Normal hearing depends on your air pressure being equal. So you're outside in your swimming pool, the air pressure inside your head, middle ear gets greater than outside your head, which can make vibrations difficult to hear. Okay, so we have the cochlea, which is organ for hearing, vestibule, which senses body position when you're not moving, and semicircular canals, which is how you know your body is moving. So the outer layer is osseous labyrinth, which is made of bone, and bony canal is filled with perilimb. So the cochlea is snail shape. It twists into three different times. So they have the cochlear duct, the two scalar chambers, and the scalar vestibule is on the superior side. The cochlear duct is where you receive the sound waves, while the scala tympani is the lower and inferior compartment. We have the vestibular membrane that separates the cochlear duct, the tympanic membrane, and spiral organs. Okay, I'm going to explain to you guys about the hearing physiology. Okay, so one, the ear, let me go back. Okay, so one, the outer funnel collects the sound wave and brings to your ear. It leads to the external auditory canal, which then hits the tympanic membrane. Um, and okay, let me get it for you guys. Hmm. Okay. And from there, the tympanic membrane is vibrated, right? So what happens? Malleus, incus, stapes. It vibrates all three of these. The oval window, right over here where the stapes is, separates the middle and the inner ear and transmit vibrations into the inner ear. Where vibration goes to the inner ears, it triggers the cochlea, and the cochlea is divided into three chambers. So it goes to the scala vestibule, which is the entranceway, then goes to the cochlear duct right here. And in the cochlear duct, the tectorial membrane starts to vibrate and it rubs back and forth on the cilia, triggering action potential that goes to the brain. And you have basilar membrane that is excess vibration gets released through the circular window. So, okay, so basically here, right, we have sound waves that are here visible and they rub against the stereocilia. So what happens is these stereocilia are attached to like this right here. It's attached to the neurons that run through the cochlear nerve. It goes back and forth, back and forth. And that's how you find out that sound. So the sound waves go through the spiral organ, causes the tectorial membrane to vibrate, which will run against the cilia and trigger nerve impulses. So yeah, that's what I said. So external auditory canal goes to the tympanic membrane, which goes to stapes incus stapes, which goes to the oval window, and then now it is going to the cochlea, right? The cochlea goes to the is it the scala vestibule, the cochlear duct, which then vibrates it. The stereocilia moves back and forth, and then it creates an action potential that goes to the brain, and it goes to the basilar membrane. So like that. That's how it is. So if your hearing loss is beyond a repair of the hearing aid, so hearing aids are basically just microphones and they kind of stimulate the tympanic membrane. While cochlear implant, they are transmit sound waves as electrical signals directly into cochlea. So the wire inside the cochlea, so whatever sound will be picked up to the implant to stimulate auditory nerve. So see here, the cochlea, they literally put a cochlea, like an artificial cochlea inside of here so that you can process sound. Okay, so let's talk about equilibrium now. So you have static equilibrium, right? It's you have the ut static. You have the utricle, which is closer to semicircular canals, the saccule expansion closer to cochlear, and each of these have little green dots of vestibule. And maculae are sensory organs, and they kind of sense static equilibrium or body position when you aren't moving. So basically, right? Um, the way it works, okay, let me go through the physiology of it. So, it sends service, like the neurons that go to the nerves, they kind of project upwards into gelatinous material called the ophthalic membrane. And embedded are called othallate, which are grains of calcium carbonate. Their job is to provide weight. And when you tilt your head, they will slide one way or another. So the macula is sitting upright. These othallets are sitting right, but tilting will cause the otolith to slide forward. This kind of stimulates your automatic nervous system because it will stimulate skeletal muscle contract to react tilting your head to maintain your balance. So the otoliths here are what kind of like tells you you have your balance. So it's like, oh, am I moving back? Am I moving forth? Yeah. So dynamic equilibrium, you have transverse canal, sagittal canal, and coronal canal. It kind of tells where your head, moving your head, and stuff like that. So you have hair cells, and they have embedded in the gelatinous material called cupula. So when you rotate your head, you will cause all the perilip inside the semicircular canals to swirl around, which will trigger cupula and trigger hair cells. So inside the apicula, it tells you your head is rotated. So there are other receptors throughout the body that maintain your balance to a lesser extent. You have the proprioceptor receptors in the neck and visual perception. So when you feel motion sick, this is when the sensory receptors are sending conflict info about your body position and movement. So vertigo kind of is like when sensory receptors that you're moving, but your body says you're not.